How does this connect to this? Hi, I'm Dave Doodling, Education Director at the New Mexico Museum of Space History. Today, we're going to explore how magnetism is everywhere. You need these materials: 30 pennies, colored tape, computer printout, refrigerator magnets. The universe has four fundamental forces: strong force, weak force, gravity, and electromagnetism. The strong and weak forces just work inside atoms. Gravity distorts space, so matter pulls together. And electromagnetism has two faces: electricity and magnetism. You probably know a basic rule of magnets: opposites attract and likes repel. And you may have tested materials to see which ones are attracted to a magnet. Paper clips, nails, needles, and the side of your refrigerator get a yes. Wood, plastics, and paper get a no. But aluminum foil and copper wire are a no, even though they are metals. Why? Magnetism is everywhere. It's just that most atoms do a good job of hiding it. Only three, iron, cobalt, and nickel, really show it by themselves. To find out why, let's dip our toes in the shallow end of the deep sea of quantum physics. Atoms have two main regions: a nucleus and a cloud of electrons. The nucleus has protons, heavy positively charged particles, and neutrons, heavy uncharged particles that help hold the nucleus together. The number of protons determines the kind of atom. 1 is hydrogen, 6 make carbon, 92 plus lots of neutrons make uranium. And for each proton, the atom will have one electron, a negatively charged particle that weighs almost 2,000 times less than a proton. In 1922, Niels Bohr worked out that electrons arrange in orbitals inside atoms. The details were a maze of confusion until 1925, when Wolfgang Pauli determined that electrons had four features, including magnetism, and that no two electrons could have the same features in the same place at the same time. Instead, they stack up in shells and subshells. Textbooks usually show these like planets circling a star. That's a simple way to illustrate a complex problem because electrons move more like this. But it's good enough to let us build a simple board game that shows how magnetism works. Print the 2 pages and tape them together. Cover the heads on the pennies with a piece of tape. This represents the positive direction of an electron's magnetic field. Lines on the board represent electron shells and subshells building outward from the nucleus. Put down 1 penny, tape side up, in the 1s subshell, and you have hydrogen. A second penny gives you helium, but the Pauli exclusion principle says the magnetic vector, the tape side, has to point the other way. That means the magnetic pull of one electron is canceled by the reverse direction of the other. Put another penny, tape side up, in the 2s subshell. This is lithium, a reactive metal used in batteries. Let's jump ahead and put another penny in 2s and 3 in 2p to make nitrogen. Electrons find each other repulsive and like to live alone, so place them tape side up in separate homes. You would expect these unpaired up electrons to produce magnetism, but atoms with unfilled outer shells combine with each other so electrons reverse and cancel. Now add pennies tape side down to get neon. Like helium, it is a noble gas, a chemical that does not easily combine with others because its electron shell is filled. You get the idea now, so let's skip straight to iron. Fill in all the solid circles, 3s, 3p, 3d, and 4s, but leave the dashed ones empty. Notice that we filled 4s before finishing 3d. Although it's a higher subshell, its energy is lower, so it fills first. That lets us have unpaired electrons that don't combine with other chemicals. If molten iron cools slowly, the atoms align with the local magnetic field to make a magnet. If it cools quickly, the atoms are random, but an outside field will make them line up. Fill a 3D dashed circle and you have cobalt, another ferromagnet. Fill another 3D dashed circle and you have nickel, a weaker ferromagnet. And then copper pulls a fast one. Instead of being a weak magnet with a single 3D vacancy, it steals from the 4s pair to fill out the 3D subshell. Copper is not magnetic, but it shares electrons so well that it is the second best electrical conductor. This skips over a lot of interesting changes in the elements, like chromium. It has 4 up electrons. Why isn't it a strong magnet like iron? It is, sort of. But its atoms flip back and forth as they crystallize, and the magnetism cancels. So chromium is called an antiferromagnet. The story is much the same for all atoms. Electrons pair or atoms crystallize in opposite directions to cancel their magnetism. Some materials exhibit odd forms of magnetism. Diamagnetism happens when paired electrons repel an outside field like this pencil lead, carbon, floating over supermagnets. All materials are slightly diamagnetic, but few repel this strong. Paramagnetism happens when unpaired electrons are attracted to an outside magnetic field. This happens in liquid oxygen, leading NASA to experiment with magnets as valves. But wait, there's more. Over the last century, we have learned how to improve on nature. First, Tokoshichi Mishima, a Japanese metals expert, added aluminum to nickel iron steel in 1931 and invented better magnets. These Alnico magnets dropped the weight of speakers by 95%. In 1966, scientists at the Air Force Materials Laboratory combined common magnets with rare earth antiferromagnets to make the first supermagnets. Today, we combine neodymium, iron, and boron to get neomagnets up to 18 times stronger than iron magnets. Long before the disks and flash drives data, music, and video were stored on plastic tape recorded as magnetic patterns in iron oxide. Research on that led to the invention of the Halbach array, where the magnetic field flips back and forth, canceling on one side and looping out north and south on the other. This is why refrigerator magnets stick and slip if you rub them the right way. You are sliding opposing and then matching fields across each other. This is at the heart of maglev, or magnetic levitation propulsion. In March 2016, the 846th Test Squadron at Holloman Air Force Base set a world record of 633 miles per hour with a 1-ton rocket sled riding atop magnets, zipping down the length of 7 football fields in 2 seconds. More sedate speeds are planned for a number of maglev passenger trains. We even use magnetism to study the human body by turning protons into miniature radio transmitters in magnetic resonance imaging. A strong magnetic field changes the spin of the proton in a hydrogen atom. When it flips back, it emits a bit of radio energy. Antennas pick this up, and computers paint a map of soft tissue that X-rays can't see. Does it seem odd to use something so big to study something so small? How about atom smashers? Properly called particle accelerators, these have grown from handheld in the 1920s to the 5-mile-wide Large Hadron Collider in the Alps. Such massive, powerful magnets are needed to help shred tightly bound subatomic particles as we probe the inner universe. And probing the outer universe, the Alpha Magnetic Spectrometer aboard International Space Station looks for evidence of dark matter. In a future video, we'll show you how copper can be magnetic and how to build a simple motor or generator, the other half of electromagnetism. In the meantime, remember that your magnet on the fridge may hold the secret to future space launches. Thanks for watching, and stay tuned for more activities in Virtual Rocketeer Academy.